Hello, welcome everyone to Colloquium today. I am very pleased to present Seáñez from the University of Washington, St. Louis. Mayo comes from a background in biomedical engineering with his bachelor's degree from the University of Texas, San Antonio, and then master's and PhD at Northwestern University and the Shirley Ryan Ability Lab, which at the time was the Rehab Institute of Chicago. Mayo then went on to work as a postdoc at EPFL in Lausanne, Switzerland, before joining the faculty at WashU as an assistant professor in the Department of Biomedical Engineering and Neurosurgery. So I'm very pleased today to have Mayo here to share his work on neuroprosthetics for rehabilitation in spinal cord injury and studies in motor control. So please help me welcome Mayo.
Thank you, Kim, for the introduction and for inviting me to give this talk. I'm looking forward to meeting all of you in my meetings today. So, as Kim mentioned, today I'll be talking about my work on neuroprosthetics for rehabilitation of people with spinal cord injury. And this is the work that I've done during my PhD, postdoctoral work, and then the research that we're undertaking now in the Seáñez lab at WashU. So I'll start by giving a quick introduction into spinal cord injury. So I think a lot of you know that it's a life-altering event that leads to long-lasting impairments, and the injury interrupts the communication between the brain and the spinal circuits below the injury, performing different types of actions. And this results in the compromised ability to control motor function, to receive sensory information, but also a lot of other problems for people with spinal cord injury, autonomic problems, sexual function, bowel, and bladder. And I have this here because the focus of my talk today and the focus of my research so far has been on the restoration and the improvement of movement. But it's not the only challenge that people with spinal cord injury face. So depending on where the injury happens on the spinal cord, there are different levels of dexterity or different amounts of control that are available to an individual. And depending on which of those are available, they have different devices that allow them to control assistive devices like wheelchairs. When the injury happens higher in the neck, and they don't have neck movements or head movements, there's a sip and puff system where people inhale and exhale in order to move their wheelchairs front and back or to turn. There's a head array if they have head movements or neck movements where they push against these switches in order to move the wheelchair, or if they have enough dexterity in the hand to control a joystick, then the gold standard of wheelchair control is this joystick control. But these devices, even though they allow people with spinal cord injury, with high-level spinal cord injury to control a wheelchair, are not great, right? So these offer non-proportional control, meaning that it doesn't matter how strong you press against the lever, you're going to turn at a predetermined speed. You can only move in one direction at a time, so these particular two. So they're not the best ways of control. And then in terms of rehabilitation, they're not doing much to promote mobility of the user. So they're set in place to require as little effort from the person as possible. They don't exploit whatever survived the injury. And even though you may not have enough mobility to control a joystick with your hands, that doesn't necessarily mean that you lost all mobility below the neck. So we could perhaps promote upper body mobility to avoid collateral effects of paralysis, to prevent muscular atrophy, to strengthen residual connections, to strengthen those muscles, reduce chronic pain, and perhaps to recover some of the lost mobility. So the focus of my work during my PhD was on the development of body-machine interfaces for people with spinal cord injury. So what body-machine interfaces are interfaces that connect the body to the control means of a machine. And we can do this by using different types of sensors. This can be motion sensors, EMG sensors, ground reaction, torque sensors, this types of sensors, and then using those to transform a high-dimensional body signal space to the low-dimensional control of a machine. So the focus of my work was on develop a body-machine interface for people with high-level spinal cord injury. This would be people with injuries at the cervical region, something that could be personalized to each individual's unique residual ability, that offers intuitive way of controlling, something that could be adapted to them as they're learning how to control the interface better, that can be adapted with them, and offering continuous 360-degree proportional control and promote mobility. So during my PhD work, I did this using two different types of approaches. So one was a supervised approach, a Kalman filter way of training this body to cursor map, where we had a cursor moving on a screen with a predetermined path, and we asked people to follow the target as if they were controlling it already with movements that they chose to control up and down and left and right. And we measured signals from as they were doing this activity. Another method is an unsupervised approach, where you don't choose how you're going to be controlling the interface. Instead, you tell people to explore their natural, comfortable range of motion. So we asked them to perform what we called a dance, 45 seconds, 40 seconds, and then we looked at the dimensionality of their movements, and we did principal component analysis to turn the first two principal components into the control of X and Y, respectively. So the top approach, the supervised approach, is a Kalman filter approach. Bottom approach, unsupervised principal component analysis, but both offer the same result, that using body movements, people can then control a two-dimensional on a computer screen. Once we had participants train on computer control, perform different types of video games. Once they were very good at this control, then we mapped their body movements so that instead of controlling a two-dimensional cursor, they were controlling their own wheelchair. So here we have one of our participants driving her own wheelchair on the first session and then 5 sessions after training. So she's wearing motion sensors on the shoulder. We hijack her wheelchair and use those to control the velocity of the wheelchair. And you can see that with practice, she's driving faster, she's taking wider, more comfortable turns, but she's still paying a lot of attention. All of her attention is on the visual feedback of this cursor. In reality, if you want an intuitive control, you would want them to focus completely on the environment and forget that they're using a new way of controlling their wheelchair. So she could still benefit from a lot of practice. So we also wanted to see, okay, so we're actually using areas of the body that normally participants are not using in their daily life. So could we use this as a rehabilitation approach? So we performed 12 weeks of training using different combinations of body-machine interface, playing video games, center outreaching, and we did clinical evaluations before, in the middle, and after training. And what we saw were slight increases in measures of white matter density in brain areas associated to motor skill learning, and these were paired with increases in strength production at the shoulders, at the upper arms. So in this work, we showed that body-machine interfaces can be adapted to individuals with different levels of residual mobility. They can offer a higher level of assistive device control than currently existing devices like the SIP and PUF and the head array. And by promoting the use of their residual abilities, we can strengthen the neural and enhance neuroplasticity. However, these improvements were limited to the body areas that still had some residual control. So we could only place motion sensors or capture motion sensor data in areas of the body that had movement, right? And even though they increased in strength production on their upper body, they couldn't do any task that they couldn't do before. So they didn't regain any functional abilities by strengthening their muscles. So how can we promote the recovery of function in areas below the level of the injury that are paralyzed? And this is where I transitioned into my postdoctoral work in Switzerland, where I was involved in a first-in-man clinical trial where we used an epidural lead, traditionally used for chronic pain management. We implanted this epidural lead on the dorsal aspect of the spinal cord under the vertebral segments T11, T12, so that with this lead, we could deliver pulses of electrical stimulation below the injury to a dorsal aspect of the spinal cord and an implantable pulse generator that we could communicate with wirelessly through the skin. So all this was a fully implantable device that we wanted to see where we could restore the ability for movement using this electrical stimulation. So the first part of this approach was to verify whether we could enable movement in muscles with paralysis. So we had participants sitting on a dynamometer. We asked them to pull against the dynamometer. We see no muscle activity, no torque being generated. Instead, whenever we turn the stimulation on, we enable this muscle activity on the agonist muscle without activating the antagonist, and then enable some torque production at that joint. We test this on different joints. We verify that where we can enhance muscle activity and torque generation for the different muscles, and which electrode configurations allow you to do that the best. After this, then we want to see where we could restore the ability for locomotion using this prosthetic effect of the stimulation. So here's one of our participants with an injury at the cervical level, classified as HSC. This participant had a total paralysis on all of the key leg muscles. Scores of 0 mean that there's not even a palpable or a visible contraction of these muscles. We have muscle activity, he's using a bodyweight support system, and here the epidural lead. So first, he tries to walk without stimulation, has a spinal cord injury, he can't activate the leg muscles, can't ambulate. But then by turning the stimulation on and alternating where on the spinal cord we're stimulating at different phases of the gait cycle, we're able to enable this person with spinal cord injury the ability to walk again. So importantly, this is a prosthetic effect of the stimulation, meaning we turn the stimulation on, they're able to activate leg muscles, they're able to walk, this is a step height, muscle activity stance. We turn it off and they lose immediately this ability to walk. We turn it back on and immediately they regain the ability to walk. We have different participants and you see this in the beginning, this prosthetic effect of the stimulation. But it's not the stimulation doing all of the work. So what we did in this experiment was to fix the stimulation parameters constant, same amplitude, same frequencies, and we asked the participant to voluntarily exaggerate the effect of the stimulation. So here he's walking with that stimulation pattern, and then voluntarily he kicks his knee higher. So he's able to interact with the same parameters of the stimulation to modulate the effect of how big those stimulation effects are. And finally, so here's the data for that. We have AMG activity, step height, and then the quantification of both on 3 different participants. And finally, another important thing of this prosthetic effect is that they can use it for very long periods of time. So here we have one of our participants at the start of the session. So he's walking on a treadmill. And then at the end of the session, after walking 1.2 kilometers in 1 hour. And what we see is that there is little to no degradation in their performance or their ability to do this very intense type of training using this prosthetic effect for a very long time. And it's in this combination of the prosthetic effect of spinal cord stimulation and activity-based training that we started observing some interesting results of rehabilitation. So this participant that had complete paralysis in the left leg started regaining some knee extension after 2 months of using this type of rehabilitation. This is importantly without the stimulation. 5 months after, this movement became much larger in amplitude, much more better controlled. He regained hip flexion, toe extension, maybe some plasticity in the corticospinal pathway, and autonomic function, so the ability to sweat. And these improvements were also paired with improvements in motor scores in leg muscles. So this is why the field of spinal cord stimulation is very interested on using this as a rehabilitation technology. And it's not only a group, different groups here as well have shown that when you pair spinal cord stimulation and training, and only in the combination of both and not either of those alone, we can start seeing ability to induce plasticity in the chronic parts of spinal cord injury. So after the end of the study, this 5-month study, the implant was already there. Everything was fully embedded. So participant asked if instead of explanting the device, they could keep it to use at home. So what we did was to combine the spinal cord stimulation, the communication system that they had, with pre-programmed stimulation paradigms that we could monitor through the use of body-machine interfaces, so wearable sensors on the feet, and the implant that they already had to allow them to do different types of locomotor activities in the commuting or in different settings. So here, someone would start the simulation on. We have a synchronous pattern of flexion, extension, and propulsion of the leg muscles, and they're able to walk with this pre-programmed stimulation. But this is all feed-forward control. So the way that we were controlling the simulation in the lab setting was that we had infrared markers placed on the hips and the knee and ankles. And depending on where the leg was with respect to the hip, we knew what pattern comes next. So we knew whether to simulate flexion, extension, or propulsion. And this is easy to do for the lower limb because it's a cyclic motion, so it's easy to predict what comes next. In the upper limb, it gets much more complicated. But talking to participants on how could we improve the delivery of the simulation, things that they told us that they wanted us to improve was the accuracy of when do we stimulate or where do we stimulate whenever they are expecting it. The ability for them to be the ones controlling the stimulation rather than us, the experimenters, being the ones to control the simulation, us pre-programming where we stimulate and when, and the timing of the stimulation. So they said whenever the stimulation came too early or too late, that really affected in undershooting or overshooting where they wanted their step to be, which then could cause trips and they would lose confidence in the system. So we think that a way to address this is by the development of brain-controlled stimulation, not only to achieve a better prosthetic control, but also to enhance the potential for rehabilitation. So there's previous studies that have shown that brain-controlled neuromodulation on rats with spinal cord injury and people with stroke have shown improved effects of recovery than just stimulation alone. So this led to the development of brain-spine interfaces. So this was previous work that happened in the lab where I did my postdoc when I started. And the idea is on non-human primates, they performed a spinal cord lesion. They implanted a monkey with Utah arrays to measure intracortical activity of the motor cortex, and then muscle activity, so that using this brain-recorded activity, they could predict gait events, foot strike, foot off, and then link those to the delivery of the stimulation patterns that enable these types of movements. So in a pilot study on non-human primates, monkeys with unilateral spinal cord injuries were able to use this brain-spine interface to re-enable this controlled locomotion. So here, the brain-decoded commands are linked to a delivery of flexion and extension, and these monkeys with spinal cord injury were able to walk again. And this is a very exciting proof of concept. But it's on one type of very specific type of locomotion, which is this treadmill walking. And in the real world, we're not walking on a treadmill, right? So what we wanted to see is how does this neural activity vary, or how could we generalize, how could we create decoders that extend farther than this rhythmic type of locomotion on a treadmill? So how does our brain control walking? How does it differ whenever we're walking over ground or in a corridor, or whenever we have to take steps of different lengths, whenever we have to navigate obstacles, go up and down stairs? So we did a study on non-human primates where we implanted 2 monkeys with Utah arrays on the sensory motor cortex, so premotor, motor, and somatosensory cortex, as well as muscle activity and kinematics. And what we want to see is how are the different brain areas associated with different levels of dexterity in the locomotor control. So something that we use for analysis that is very important is the firing rate of each of either our single units or our channels. So I'll go into how do we create that. So normally when you're looking at a channel, what you see is something like this, where this is voltage, and you have individual firings that cross a threshold. So you place a threshold based on the noise. You make bins, and what we're interested in seeing or measuring is how many times do you have threshold crossings per a unit of time, or per second. So that, for example, here in the beginning you will have 0 spikes. The second part you have 2 spikes per second, and then 4 spikes per second. And doing this over and over again over time, you can create a firing rate curve as a function of time of that individual unit. And if you want to look at the activity of multiple units, then a nice way of representing this is by having this color-coded. Think about it if you're looking at it from the top, so a top view of this, that would look something like this, and then you can organize a lot of different channels together so you can look at the activity of your multi-electrode array in time, the firing rate of your multi-electrode array in time. So we look at the activity of our different cortical areas during behavior. So what we do is that we sort them according to where they peak. So this would be the maximum, where they peak in time. And what we see is a very nice correlation. So we can identify neural correlates of brain activity with different phases of behavior. And we see this all across the board. For the different tasks, we can find neural correlates. So this means units, single units, that are correlated or they're maximally tuned with either the stance phase, with the swing phase, foot strike, and foot off. And you see this all across the board. But how consistent are actually these correlates across locomotor tasks? So here we're ordering for each individual task, the units, we're ordering them by the order in which they fire within that individual task. So what happens if you use the order that they fire in during the corridor task for all of the other tasks? And what we see is that you start losing this very nice synchronized activity that we have seen before. In order to quantify, what we do is that we have the firing rate of each individual neuron. We look at where the peak in the gait cycle, or where the peak of that unit is in the gait cycle, and we look at the correlation across the tasks. And what we see is that the neural correlates of behavior vary a lot actually in premotor cortex, and they remain stable for somatosensory cortex. So they're very highly correlated for the somatosensory area. However, this looking at activity of individual neurons is not done very much anymore. So a lot of groups have shown that muscle activation patterns are likely the result of the combination of activities for multiple neurons at the same time rather than the activity of each individual neuron. And these activity of combination of neural activity of neurons is typically embedded within low-dimensional neural manifolds. So we wanted to look at this population activity of the different cortical areas as the monkeys were performing the tasks, the different locomotor tasks of varying complexity. So what does this look like? Here, say that in this example, we have 3 individual neurons, so you have the firing rate for those individual neurons. You could imagine that you could plot the activity in 3 dimensions of those neurons, and you have a population trajectory. So the plane or the low-dimensional subspace where most of this activity resides, this is called the neural manifold for that task. So the first thing that we ask is how similar are these neural manifolds across tasks? So we identify the neural manifold for task A, we identify the neural manifold for task B, and then we combine the neural manifolds whenever you combine all the tasks together, so that we look at the dimensionality of either one individual task versus the dimensionality of all individual tasks. And our hypothesis is that if the population activity resides within very distinctly aligned neural manifolds for each individual task, then whenever you combine all the tasks together, the dimensionality of that combined neural manifold will be much higher than that of individual tasks. Instead, if the neural manifolds across tasks are very well aligned, they happen over neural manifolds that are almost the same, then whenever you combine all those tasks together, you won't gain much by combining them. So the dimensionality will still be low dimensional. So this is what we saw. In the premotor cortex, we see that the dimensionality of the neural manifold with all the tasks combined in yellow is higher than that of individual tasks. So individual tasks are in the gray scale. Instead, in somatosensory cortex as well, the combined neural manifold dimensionality is much closer. It's very low dimensional. It's almost the same as if you're just using one of these tasks together. So we quantify this difference in dimensionality, and this is what we see, that the task-related neural manifolds are very uniquely aligned in premotor cortex, somewhat aligned in motor cortex, but they're very, very similar to each other in somatosensory cortex. So finally, we wanted to identify, okay, what part of the activity is related to the task itself, and what type of activity is uniform across different types of locomotions. So what we use is this technique called the mixed principal component analysis, where you can detangle your population activity into neural data that is independent to the task, so that regardless of what locomotion task you're performing, you see this activity across locomotor tasks, and that activity that is specific to a task. So this is a task-dependent neural modes. So we measure how much of the variance is captured by each type of information on the 3 different cortical areas. And what we see that in the dorsal premotor cortex, most of the activity is actually represented by task-dependent neural modes. Instead, in primary somatosensory cortex, most of the activity is task-independent. Now, how is this information useful whenever we're trying to build decoders? So what we would want to build is a decoder that we can train on an individual task and then is able to generalize across other tasks that we're not able to train for, so that you're able to train a decoder in the lab, but you're not going to be able to predict every possible situation that you might encounter outside of the lab. So what we do is that we build a decoder on the corridor task projected into this neural manifold containing all the tasks, and then we're trying to see where this population activity resides. We test its ability to generalize them to all of the other tasks that this decoder was not trained on. And what we do is that we start removing either task-related information or task-independent information. And the hypothesis is that the decoding accuracy of behaviors that can generalize all across the tasks will decrease proportionally to the number of neural manifolds that are task-independent. So if you remove information that is task-independent, that it's consistent across all tasks, you will lose this ability to generalize across tasks. And this is what we found on 2 monkeys on the 2 columns. So it's our initial ability to generalize whenever we project onto the full neural space manifold. And then we see that whenever we start removing task-dependent information, so this is the light green, we don't lose the ability to generalize. Instead, whenever we remove the task-independent information, we very quickly lose this ability to generalize across tasks. So, in summary, spinal cord stimulation offers a prosthetic effect that can enable the activation, the voluntary activation of paralyzed muscles. This prosthetic effect enables the prolonged and voluntary control of the stimulation, the modulation, the voluntary modulation of the prosthetic effect. Long-term practice in the combination of spinal cord stimulation and activity-based training has resulted in increases in measures of function in chronic spinal cord injury, and brain-spine interfaces can be used to bypass the lesion and link brain activity to a delivery of stimulation programs, and we may be able to build decoders that can generalize across different types of locomotions. But there are some limitations of these. One, obviously, it's the invasive nature of this technology, which may limit the interest of different people on wanting to adopt this technology. The other is that all this is very high-tech, it's very expensive, it requires a very high team of experts that can dramatically increase cost and reduce access to the spinal cord stimulation technologies. So the questions that we're trying to solve in the lab now at WashU is always with this idea of restoring movement on people with spinal cord injury with different questions in mind. So one is, how can we improve access to the spinal cord stimulation technologies? How can we expand the repertoire of what is available through non-invasive methods? Trying to understand what are the mechanisms of plasticity that are driving this recovery, and then how could we re-enable this voluntary control of movement non-invasively? So we have built the lab with different technologies that allow us to ask these types of questions. We have body-machine interfaces. We use currently non-invasive spinal cord stimulation. We have wireless motion and EMG sensors. We use a hybrid markerless and marker-based motion capture system where we could either use infrared markers or just video-based tracking. And we develop our own in-house software to visualize the EMG responses in real time. So I'll start by the first project on how can we improve access to these spinal cord stimulation technologies. The current way that we're undertaking this approach is by using a conventional method called transcutaneous spinal cord stimulation. So this is a method used by different groups where spinal cord stimulation is delivered through the surface electrodes conventionally at a continuous frequency, a continuous amplitude at 30 hertz, so that we can use this effect in order to enhance or enable some sort of movement. So that then we would use body-machine interfaces or these wearable sensors to capture whatever movements we enabled and then turn those into the two-dimensional control of a computer cursor. Once people can control this computer cursor, then instead of moving the leg over and over again as a rehabilitation strategy, to use video game control as a rehab. So this spinal cord stimulation assisted movements as a rehabilitation strategy. So we have been working on the development of this body-machine interface, where we have participants wearing these motion sensors on the leg. So it's actually a student, not a person with spinal cord injury. And what we do is the same thing. We ask people to just move, explore their range of motion, and we capture their ability to move in different dimensions. And we turned the two first principal components into the control of X and Y. First thing that we do whenever they're controlling the interface is for them to do a traditional center-out reaching, where now they're using their legs to control this 2D cursor, and we have them reach on different targets in the periphery. This would be very boring as a rehabilitation strategy, but what we're interested in seeing here is that while they're using their legs to control this two-dimensional cursor, we can study different aspects of their movement. So we look at their trajectory of their movement, at the velocity of their movement over time, so as they practice over blocks, and we can quantify different performances that allow us to understand how is it that they're learning to control this interface. Are they getting faster, more accurate, straighter in their movements, or are they reducing their error? But what we wanted to use as a rehabilitation is this gaming, right? So we adapt different open source games that each require a different level of control. So we have video games that require participants to make very precise movements without deviating from a predetermined path. We have others that require them to remain stable and only move in the right direction at the appropriate phase of movement This one is very challenging in the beginning because they don't understand the map between body motions and cursor movements. So they really have to have a good understanding of this internal model. Others that are a bit less time restrictive, they just have to match icons. Others more dynamic, where they have to move this paddle at the appropriate time. And then we do all of this practice in an environment where we really want them to focus on the actual video game itself rather than on how is it that they're controlling this interface. So now we recruited people with spinal cord injury. First part of this was to verify how much activity could we enable with the use of non-invasive spinal cord stimulation. So here we have one of our participants without spinal cord stimulation, no muscle activity, no joint movement. He's asked to move the right knee. With the stimulation turned on, he's able to regain voluntary control of this knee angle. And I have voluntary under an asterisk because the instruction was to extend the right knee, but it's actually the left knee that he's extending. And even though he was aware of this mismatch. But we verify how much movement can we enable with this non-invasive spinal cord stimulation. So that then we have them actually using the stimulation during the control of the body-machine interface. We're using motion sensors, and we quantify how much do they improve in center-out reaching whenever they practice with conventional center-out reaching trials, so one full session of 5 blocks of center-out reaching versus one equal time session, so 45 minutes, instead playing video game control. And what we saw is on participants without spinal cord injury, regardless of which type of training they do, either reaching or gaming, they improved to the same amount. So they're able to improve by the same amount. And in our participants with spinal cord injury, so they're also able to improve on both types of training. Here we have a bit of a different initial performance. So this means the calibration was not great in the beginning, but importantly, even though the calibration was not ideal in the beginning, he was able to learn this non-intuitive map between body movements and cursor control that at the end he had a good performance in the training. So how can we expand the repertoire of functions enabled by non-invasive technologies? So to ask this question, what we do is that we have participants sitting supine, we have a stimulation electrode, our return electrodes, and we look at the ability of the spinal cord stimulation to activate different leg muscles. So what we do is to create recurrent curves for the activation of the leg muscles, where we're sending pulses of electrical stimulation of increasing amplitudes going down, and we're measuring the muscle responses to identify 2 things. One, the motor threshold of the response, meaning the lowest amplitude at which you get a response, and then the saturation level of the response. 1 or 2 things. Either whenever the amplitude of this response no longer increases, that it saturates and remains stable, or whenever the stimulation is so high that your participant tells you that we ask them to tell us when it's uncomfortably high, and they don't want to go higher. So this gives us a curve of the muscle response as a function of the stimulation amplitude, and we call this the recurrent curve for that muscle. So we do this for all of the leg muscles at the same time, where we can plot the recruitment of the different leg muscles as a function of the stimulation amplitude. And what we see with the use of this conventional single electrode transcutaneous spinal cord stimulation is you are able to activate the different leg muscles, but you don't have a lot of control on which muscles are active and which ones are not. Now, why would this be a problem? So say that you wanted to target the right ankle muscle, so tibialis anterior, medial gastroc, and soleus. With this configuration, by the time you're activating you would want to be at an amplitude about here, but at this amplitude, you're already significantly recruiting a lot of other leg muscles. So this would mean that you have a lot of co-contraction or unnecessary activity on muscles that you don't want to be active at that part of the training. So our approach was to see whether we could enhance the ability to selectively target different muscles by using a multi-electrode configuration, with the idea that because of the motor neuron pool distribution of the different leg muscles on the spinal cord, we could, instead of having this non-selective recruitment by the single electrode configuration, maybe use this multi-electrode configuration to, for example, use the right rostral electrode to target the right leg proximal muscles and the right caudal electrode to target the right ankle muscles. So we collected data on 16 non-impaired participants and looked at the probability of activating different leg muscles on different electrode configurations. So here what we see is for this electrode location, the probability of recruiting the different leg muscles from the left leg and the right leg across the 16 participants. That then we project back onto the motor neuron pool distribution on the spinal cord, and we can create this map of spinal cord activity by that muscle. Importantly, this map is agnostic to where we place the electrode. It's just recruitment of probability projected back into the probability of motor neuron pool activation. And what we see is that there is a nice match between where we place the electrode and where on the spinal cord we see our activity. So next we want to see, okay, how selective can we be with this stimulation? So we repeat the recruitment curves for the different electrode locations. This is one participant, one electrode location. And what we see is that we can indeed first recruit the muscles that we were targeting. Importantly, it's not only those muscles that we're targeting. So we also have the unwanted recruitment in this participant of the same muscles from the contralateral side. So this is the medial gastroc, TA, and soleus of the left leg. And we always saw a combination of that, either the same muscles of the contralateral side or the ipsilateral muscles, but either proximal versus distal and distal versus proximal. So we wanted to quantify then this amount of selectivity. So we use a measure of a selectivity index, which is a measure of how much we're recruiting one muscle, so this muscle, compared to the average recruitment of all other muscles, where a positive value would mean that you're more selective to that muscle than the average. A negative value, you're worse than the average. The first thing that we do is to look at different rostrocaudal levels to identify for each muscle which would be the optimal electrode configuration if we wanted to selectively target that muscle. So here we identify, here is a color-coded electrode, which of those electrodes can target that muscle best. Then we compare the selectivity that we can achieve with that optimal electrode with the conventional approach. And overall, for most muscles, we saw that we could enhance the amount of selectivity that we can achieve with this multi-electrode configuration. And then finally, so this is promising, it's a good start, but we wanted to understand the mechanisms of this activation. So is this a reflex response? So is this mediated by posterior root muscle reflexes? Now, what this means is that the first thing that you recruit and the way that you get activation is by recruiting the sensory afferents, which then synapse to the motor efferents and then activate the muscle. Why is that important? From the beginning, if we remember, if you want the ability for people to send supraspinal input, the sending voluntary input, and interact with the effect of the stimulation, it's important that this is sensory so that you can interact with it before the synapse. Also, you allow other reflex circuits to interact with the stimulation. And second, you avoid fatigue. So if you stimulate the motor efferents directly, you will, first of all, get a one-to-one response between your stimulation and your muscle response. And second, you might get a very nice effect in the beginning, but it's going to be hard sustaining large forces and sustaining them for a long amount of time. So it'll be harder to use this as a rehabilitation strategy. So what we do is that during this recurrent curse, each pulse that we were sending wasn't actually a single pulse. It was a double pulse paradigm, 33 milliseconds apart, so that what we would expect to see is if it's posterior root recruitment, what we would see is a response, muscle response to the first pulse of stimulation, and then because this pulse has to go through a synapse and there's post-activation depression, a depletion of neurotransmitters at that synapse, you will not see a response to the second pulse of the stimulation. Instead, if you're recruiting directly to the anterior roots, what you will see is a one-to-one response between your stimulation and your muscle response. So here is what the data looks like for the recruitment curves for the different leg muscles for the first pulse of stimulation and then for the second pulse of stimulation. What we see is that across the board, we do see an amount of suppression for the different leg muscles. But the amount of suppression is inversely proportional to the stimulation amplitude. So the higher the stimulation amplitude, the more likely you are to recruit the motor efferents directly. So we quantify the amount of suppression at the worst case scenario, so at the highest stimulation amplitude. And what we want to see is a value lower than 1, meaning that the amplitude of the second response is smaller than the amplitude to the first response. And for all of our optimal electrode configurations, we find that there is a significant amount of suppression, suggesting that these are indeed recruitment through posterior root afferents. Okay, so the last project that I wanted to talk about today is on re-enable this voluntary control of leg movements. And this is through a non-invasive approach. So the idea is the same, is to develop a brain-spine interface, but non-invasively. So the idea here is to use an EEG cap where we can decode movement intention whenever someone is trying to move their limbs, and then link this decoded movement intention to a delivery of transcutaneous spinal cord stimulation in order to enable brain control leg movements. So we have started on the development of this non-invasive brain-spine interface. The first part of this was to identify what are the patterns of activation that we see whenever someone is trying to move their legs. So we have participants sitting in front of the screen, extend the right knee, and we look at where the activity happens. And what we would expect based on previous literature is that we would see activity on the central to contralateral side, so wherever the knee and the leg is, contralateral to where the movements are. So it was the right knee extensions, so we would expect to see the activity somewhere here. So first thing that we look is at this difference in frequency power between when someone is moving and when someone is resting. So what we would want to see is a desynchronization or a loss in power, which here is represented by the R squared, which is not exactly that, but it's related to that. And we see this activations of this topographical organization of desynchronization activity related to movement versus no movement. The other thing that we want to see is to identify which frequency bands do we see this modulation at. So if we wanted to build a decoder, these are the ones that would be more likely to be predictive of leg versus no movement. Now, importantly, so one of the problems with EEG is that these could be movement artifacts. So they could actually be related to movement on the EEG cap, not actually movement. Also, we have a problem that people with complete paralysis will not be able to activate the leg. So we will not be able to measure whenever they're actually moving. We would have to have another strategy to train these algorithms. So what we do is that in other blocks in the same session, we have participants not actually move, but just imagine moving their legs. We look at the activity whenever they're imagining moving the legs, and we see this nice symmetry in the relationship between the activity, the topographical organization of the activity, this loss in frequency, and the frequency bands at which we see this. Now, we're not just interested in classifying whenever someone is moving versus whenever someone is not moving. What we want to do is to turn on the stimulation whenever someone starts thinking about moving. So what we look after is on when do you see this change in power. So here we have repetitions of leg extension, knee extension. We have on the y-axis different frequencies, and then the color is represented by power. So what we look for is this big change in power between when someone was not moving and someone started to move, this loss in power, this desynchronization. And we use this time-based change to build decoders so that we can predict whenever someone starts to move. So we do this by using an LDA motor state classifier that at each point in time, we have a probability estimate of whether someone is moving or someone is not moving. And we can train a decoder with movement data whenever someone is actually moving, and then use it to predict the other untrained trials. And what we see is that we can predict pretty well whenever someone is moving their legs. So we could use decoders built on an individual moving their legs to predict whenever they will move the legs. This wouldn't tell you whether it would work on people with complete paralysis. So what we do is that we use the same decoder to test then on imagery. And what we see is still not as good, but still acceptable levels of performance. So now we move to the real challenge, which will be the asynchronous use of this decoder. What this means is that so far the way that you create this data is that you have participants sitting on a screen, you tell them rest, focus, move. So you have a cue that tells them when to start all this. In a rehab setting or someone using this in their own home, you would not have this, you don't know what they're going to want to do. You just have to have this open loop and have it perform well whenever they actually just think about moving. So what we do is to have no cues and then have just participants extend the leg and see where we could generalize to them moving freely. So here is one of our participants, and we see is, for this participant, what I would call terrible performance. So we're predicting all of the time, and we're not able to predict very well whenever they're resting. So pretty much we're over-predicting that they're moving, meaning that we would be sending positive stimulation all of the time, even though they're not trying to move. So it would probably be detrimental to their training. So we have repeated this type of training of decoder building now on a few participants. So we have 3 participants so far. Here we have the performance. Overt movements means participants are actually moving versus imagery. We see decrease in performance, not too drastic, but somewhat stable. And then on free, so this was the worst participant so far. For the other 2, we don't see as drastic difference in performance. We did change something in the protocol where we interleave the types of tasks that we did rather than have the generalization all the way at the end and after some interruption. That seemed to improve performance, but we'll still have to see whether this is consistent across participants and then finally on people with spinal cord injury. Okay, so with that, I would like to thank the lab members that actually do all of this work. I'm just presenting it here. My collaborators in the Division of Neurotechnology at Washington University, and then collaborators in all other departments and outside of WashU, as well as my funding sources supporting this work.
I would like to apologize to Washington University for calling them the University of Washington, St. Louis. You can understand my confusion, but yeah, so please, like to open it up for questions for our speaker. You can just call.
I can say that I'm guilty of the same. Yeah.
I had a couple of questions that are kind of more related to like experimental design and results. One of which was about the clinical trials. I know it's usually pretty hard to get like consistent populations of spinal cord injury patients. Were you like selecting for any parameters like time after injury level or severity or any of that?
Yes, a lot. There was a lot of selection for the clinical trial with 3 participants on the epidural trial. So the criteria for recruitment was ASIA C, D, or B. It was people who did not have any other like chronic problem that would have inhibit them from participating in locomotor training. People that could already walk or stand with some sort of assistive device, and that were active, so that would either do some sort of training in their homes. So this required a lot of the screening of a lot of participants, that it was almost like setting ourselves up for successful outcome, right? From the study, something else that we realized was, one, there was a participant with chronic pain, that it was not an exclusion criteria before. Just placing them in the bodyweight support system made this a lot worse, and then turning the stimulation on made it even worse, that we could not continue with the therapy. So we then excluded this participant. Now, not me, but the same group has repeated this type of study on people with a higher level of severity with ASIA B and A, and they have shown also the prosthetic effect in the beginning of stimulation, and it's very, very impressive. Other groups have also, the group of Susan Harkema has recruited people with ASIA B, and they're able to also show this recovery in the chronic part of spinal cord injury. And then, sorry, the question I didn't understand, it was all chronic spinal cord injury. So in this study, it was 4 years, the earliest, 4 years after the injury. And so far, I think most people have done chronic, which is where you would expect to see the least or no recovery. That's why it's exciting. But I think the real potential here will be probably intermediate spinal cord injury.
And then I also had one other question. During the implantable studies, you had mentioned seeing improvements in like the knee extension and some of the autonomic like sweating and all that. Have you done, or are people planning to do studies with either like the non-human primates or rats or something to see maybe what tracks might be growing, or if they're growing
Yes.
or just synapsing differently than before?
So we have just received funding to look exactly at this. So something that we don't understand very well right now is so a lot of groups have identified that there is some sort of plasticity going on, but what are the mechanisms of this plasticity? So previous work on rats and mice, where you can really look at these mechanisms. So you can use optogenetics for stimulation, DREADS for activation or inactivation, and what they have seen is that stimulation of pyramidal neurons enables locomotion after the spinal cord injury, so with the stimulation. Then after a spinal cord injury, a lot of the corticospinal projections are interrupted, but actually a lot of reticulospinal projections are spared. And then if you, after the recovery, after the rehabilitation, if you inhibit these reticulospinal projections, even though a rat was already able to walk again, you inhibit them with CNO, and you lose this ability to walk. So a combination of corticospinal, reticulospinal, spinal circuits are probably involved. Right now, the idea is to understand which are those mechanisms. And not only to know and to identify them, but what I think is that if we can identify which mechanisms are responsible for this plasticity, and then you can understand for a particular individual which of those are still available to them, then you could target the therapy by different rehabilitation strategies that recruit one versus the other. So hopefully in 5 years we'll know a bit more about that.
Super interesting, thank you.
Thanks. Yeah?
So my question is on the decoding work that you showed, so the different kinds of tasks.
Mm-hmm.
I'm really, really fascinated by the fact that the task invariant information was actually still useful. So at least in the upper limb, a lot of the people, those dynamics that kind of are very consistent regardless of the task tend to actually not have very much information in them about the movements going on. So it's really interesting to me that it actually does seem to be useful for the lower limb. So I don't know, can you maybe comment, like what is the distinction, right? And sort of what do you think is going on in the neural computations?
Yeah, so I think, I don't remember reading someone trying to use either the task independent to generalize. So I think if you use task independent information for getting specific activities within a task, it might be a bit difficult. One thing that I think it's different for locomotion is that if you look at a kinematic parameter during locomotion, you will find two that look exactly like these. So these parameters look very similar to what you see in locomotion. So locomotion is a very cyclic activity, and it's really a repetition of different joint movements, but very, very consistent. And even though it's different types of walking, it's still walking, right? In upper arm reaching, I would argue that even in 2 dimensions, an extension is very different than a flexion, for example. Going left is very different than going right. So there might be more task variance that then it's harder to create decoders that generalize with that type of task variance. Although what I have to say is that looking at the dimensionality of the combined manifolds, so the neural activity is equally rich as whenever people doing center outreaching and combining different tasks look at the dimensionality of the cortical area. So there's the same type of complexity in the activity there. Yeah.
Just follow up on Amy's question. I was fascinated by you said the sensory cortex seemed like it was pretty preserved across the different types of locomotion, but the motor cortex wasn't. Just wondering if you have any insights into why that would be.
So let's see. No real insights, more like inklings or what I think it's happening. So my thinking and looking at this data is that, so if you see most of the neurons on S1 are tuned right at the foot strike, like a very large portion of them are at foot strike, which is all these and all these, or foot off. So they're very kind of sharp types of events. That what I think is happening is that maybe the sensory cortex, what it's doing, it's monitoring that everything is okay. that if we would perturb the system, if something goes wrong, whatever the step, then you might see a much bigger involvement of the sensory cortex. But as long as everything is going according to plan, it's just okay, like everything. But all that is way farther than what my data can shows.
Spinal cord is handling most of the local sensory feedback and things that make it to S1 are just big events, like you say, the foot hit the ground at the right time and slip. Something that's an obstacle to be tripped on or something. Yeah.
Maybe, yeah.
That's
Sure.
totally unrelated question. No one else wants to go. So I loved your idea of training the muscles in the game environment.
Thanks.
And I was curious to hear more about what some advantages could be. Why not just have them do actual movements and watch the movements? What would the advantage be? I think you said you took like the first and second principal component and transfer that into game cursor control. So where are you going with that in terms of?
Wait, sorry, I didn't get the. Could you repeat it?
So the human with the EMG and accelerometers. I thought you took first and second principal components, and those became the two cursors.
Yeah.
So I guess why do that transform and train in a game environment rather than just say watching the leg joints or something?
So that's the main difference between the supervised and unsupervised approach. So the advantage of the supervised approach, where they choose their own movements, is that it's very intuitive way of controlling it. The disadvantage is that you cannot have a one-size-fits-all map. So you can't have a movement that controls X and Y and another movement that controls, or one movement control X and one movement control Y, because some people might not be able to make that movement. The advantage of principal component analysis is that it doesn't matter what type of residual activity they have, or whether they can actually isolate one movement, you can still, as long as it's more than two-dimensional, you can still find these two principal components that are orthogonal, so they can move independently on one versus the other. The other thing that I found on the study where we compared both types of controls is that the Kalman filter is very easy in the beginning, it's very intuitive, but it's also not very robust. That it was very prone to changes in posture, that people during the training, they would start slouching and they would have to recalibrate again and not recalibrate, like do the calibration again, just tear the sensors again and again and again. And because we incorporated the dynamics as well, the position, velocity, and acceleration of the sensors, the control was a bit harder to control. The cursor was a bit harder to control, so they would overshoot and undershoot a bit more. The PCA, in the beginning, it's always complicated. So in the beginning, it's very difficult, but people get very good at it. And I would say that it's more consistent. But even at the end, when they become experts, if you ask them how they're controlling the cursor, they can't verbalize how they're controlling it. They just show you like a combination of movements that then the cursor moves straight. I think both have their pros and cons.
We can take one more question if there is one. Yeah, go ahead.
Hi, thanks for a riveting talk. I wonder if when participants played Angry Birds and like other games in UWECE Center Out, did you see other advantages to using games other than Center Out, like engagement?
Absolutely, yes. And like it was a completely different attitude from participants doing a center outreaching that you can see the boredom in their face. And the video games, they're engaged and they're competitive. They ask, hey, what's the highest score so far? And they enjoy it. Although what was interesting is that it was different games that people enjoyed. Some found, for example, the maze, some found it very frustrating, but then other participants that improved actually found that very rewarding. That the first trial was very difficult, and then they're like, oh, I think I understand this. So it's just as a training strategy, I think the video games are much more engaging than center outreaching. But what center outreaching allows us to do is to understand what's going on there. And we could do other types of experiments where we perturb in this control space to probe different motor control strategies.
And I assume they would have played those games before too, right? So some sort of prior would have primed them.
Yes, I think there's probably, that would definitely affect their performance on the game. When you don't have to explain to them how to play the game, they will probably already start at a high level.
All right, let's thank our speaker today.